hit record. Okay, hello everybody, thanks for tuning in. Thanks for agreeing to give this talk. So today we have the second installment of our new initiative of virtual talks on time, temperature, and chemical potential dependence in quantum field theory. We are very happy to have Paul Chesler from Harvard Blackpool Initiative, who's going to tell us about detecting quark-matter cores with binary neutron star mergers. Paul, please take it away.
Hi, everybody. I will not talk about any quantum field theory here today, actually, or temperature or mu dependence. Well, almost no field theory at all. I'm going to be mostly just talking about the feasibility of detecting quark matter, or more generally exotic matter, in neutron stars with LIGO, observing the Inspirals in particular. So the one quantum field theory slide that I will have, well, kind of quantum field theory slide I will have, will just be that of the common law QCD phase diagram. If you just Google this and do a search for Google Images, you'll come up with some variation of what I've shown here. This is a phase diagram as a function of temperature and chemical potential. At low temperature and moderately low chemical potential, the phase diagram of QCD contains hadrons, things that we are built out of, protons and neutrons and things like that. It is believed that at high temperatures and high chemical potentials, well, it's not just believed, but at high temperatures and high chemical potentials, you can do reliable calculations in QCD using perturbation theory, where the relevant degrees of freedom are a deconfined state of quarks and gluons. It's quark matter, if you will. And it's believed that at intermediate temperatures and chemical potentials, there's a line of first order phase transitions here, which is this sort of curvy line that you see here. So the common belief as well is that neutron stars sit down here at this very bottom in this sort of yellow shaded region here at very low temperatures and very high chemical potentials. Whether or not neutron stars cross into a phase transition of deconfined quarks and gluons is unknown. I should emphasize as well, whether or not there is a phase transition in and of itself is also something that is not known. It's just a common law belief. So the question I want to address today is simply, can quark matter be detected with LIGO? If we observe a bunch of neutron star mergers, what is the possibility? Is it feasible to detect quark matter with LIGO? And I'm going to, because I'm asking this question about feasibility, I'm going to be focusing on perhaps the most optimistic of scenarios to detect quark matter. Obviously, you can tune parameters so that it'll be almost impossible to detect. So I want to focus on what is the easiest scenarios to either detect or exclude using gravitational wave observables. So that's my quantum field theory slide. Well, I guess I have a little bit more here. How does the phase transition affect the structure of neutron stars? So in particular, I'm going to look at strong first order phase transitions where also the surface tension between quark matter and hadronic matter is very large, in which case if I just plot the energy density as a function of pressure in this upper left-hand corner plot, so at low pressures, the equation of state will be that of nuclear matter. At high pressures, it'll be that of quark matter, and you'll see this jump here in the energy density rho. That jump will be a latent heat. You also see in this sort of cartoon plot here is that the slope of rho in the rho p plane is different in the quark matter phase. what the phase transition results in is a latent heat as well as a different speed of sound. The speed of sound is related to the derivative of rho with respect to p. So, which you should expect for neutron stars, and I'll show this just in this right-hand cartoon here, is there'll be a mantle of hadronic matter, and then in the core of the neutron star, where the pressure is its very highest, there'll be a quark-matter core, at least if the phase transition happens at sufficiently small pressures. So the latent heat is expected to be positive. I think we don't really know what the sound speed is going to be, but it is reasonable to surmise that it's going to result in a softening of the equation of state. And if that happens, then in the MR, then your MR curve should look something like what I've shown here on the bottom right here. So this blue curve is a candidate nuclear equation of state, the MPA1 equation of state. The MR curve associated with that equation of state goes up to about 2.5 solar masses before the neutron stars become unstable. The dashed line here show regions where the neutron stars are unstable to collapse. That happens whenever the slope of the MR curve it becomes positive here. So if there is a phase transition, then at some neutron star mass I'll call MC, it'll be the critical mass. That'll correspond to a critical pressure in the core, in the interior, the very center of the star. At that point, you'll start nucleating quark matter. And because there's a latent heat, and because the speed of sound is probably less than that in nuclear matter, what generally happens is that R, the radius of the neutron star, must decrease more rapidly as M increases, okay? So you have this sort of kink, excuse me, this sort of kink that develops in the MR curves. If the latent heat is sufficiently large, the slope of that kink becomes positive, and the core will in fact become unstable to collapse, and therefore your stable branch of your MR curves will just terminate at this mass MC. Is everybody on board with me here? I'll take your silence as a sign of approval.
Yes, we have muted microphones.
I know, I understand that. It's not like you're in a regular seminar where everybody can nod their heads and I can see. So I'll just take the silence as the sign of approval. All right. So at the end of the day, though, the message
because on the blue part, the slope is also positive, right? So that indicates stable stars.
Yeah. Sorry. Yeah. Right. Those are stable. Right. It's only
so
when
it's not only the slope. Eh?
It's not only the slope. Yeah, it's the double valuedness of it. That's right. Thank you for asking. Right. It's double valuedness of it. And I should say also that there are, depending upon the details of your equation of state, you can have disconnected MR curves as well, where for this green curve here, there's sort of a dashed region here where the neutron stars are unstable. So there's sort of a gap in the allowed radii. The bottom line message that I want to leave you with here, though, is that the signature of quark matter, or really any sort of exotic matter, could be something else like hyperons, is that there's a kink in the MR curve. Okay, that is how the phase transition can affect the sort of the structure of the neutron stars. Now, what does LIGO observe? What are the most easily accessible LIGO observables? Well, there are the masses M1 and M2. Those have some significant errors associated with them, but they are things that LIGO can measure. And the typical errors associated with them are going to be fractions of a solar mass. There's the chirp mass, the script M here, which is this combination of the individual masses M1 and M2. It is probably what LIGO can measure with the greatest accuracy. So for the purpose of today's talk, the errors associated with the chirp mass are essentially 0. I should say, by the way, that I'm going to assume throughout this talk that M1 is the greater of the two masses. The next observable that LIGO measures with some degree of fidelity is the so-called mass-weighted tidal deformability, this lambda tilde quantity. It is just the individual tidal deformabilities of the neutron star, lambda 1 and lambda 2, weighted by some combination of the masses. The lambdas themselves measure how the neutron star is deformed by the gravitational interactions with its neighbor. So here's a nice spherical neutron star here. It'll be deformed by the gravitational interactions with its neighbor, and that deformation, at least in the linearized limit, is determined by these parameters lambda 1 and lambda 2. So what LIGO measures best is not the individual lambdas, but this lambda tilde. So how does the presence of a quark matter core manifest itself in lambda tilde? You can go ahead and construct a bunch of models for quark matter equations of state and hadronic matter equations of state and see, and people have done this, and what they concluded is that there's a remarkably useful universal relationship between the neutron star's compactness, c, which is defined to be the mass divided by the radius, and this tidal deformability. And I should say that I have not included all the references here that have derived this formula. There are several other papers, including one by Alexei, that also work out these formulas here. This compactness versus lambda formula here. So c is quadratic in log of lambda, and these are these coefficients here. And this relationship holds for quark matter, for hybrid neutron stars with a quark matter core. It holds for neutron stars with just hadronic matter. It's completely general, and it holds at about the 7% level or better. So here's a plot on the right-hand side of this relationship.
A question?
Yeah, go ahead.
What is there some simple way of understanding this relation, or it's just a phenomenological observation for
as far as I know, it's phenomenological. I don't know if there's a simple way of understanding it. There probably is. Whenever something like this happens, there's probably a simple way of understanding it, but I don't have it at my fingertips. I mean, go. Sorry.
Yeah. So I also have a question, because I remember that if you include the crust equation of state, then for the compactness going to zero limits, lambda actually goes down, right? So in your model, do you consider the low density part? You do use any like BPS crust equation of state, or you just stick with pure?
I'm sticking with what has been worked out in the literature. You can look at this paper by Carson and company and see that this holds at the 7% level. 7%, okay. 7% level or better. Right. Okay. And so the general trend here is that as the compactness increases, okay, lambda decreases. And that I think is easy to understand. As the compactness decreases, the star is getting smaller, and therefore it's becoming more point-like, and it's more difficult to deform it. It's more gravitationally bound together. So that I think is a straightforward consequence there. Now, if we now look at our MR curves that I showed you before, these are just sort of, you should regard these, by the way, not as being precise in any sense, just caricatures of what we should expect. At the end of the day, because the stars are getting compacter, the compactness is increasing, going along the quark matter branch here, this connected branch that's black, what you should expect then in lambda is a kink that occurs at m equals mc at your critical mass, okay? And in particular, lambda should decrease more rapidly, okay? All right, so that's just simply, again, because the neutron star radius is getting smaller more rapidly as a function of mass. So you get this kink. That's sort of the signature that we're looking for here. Now, so the game plan here, and this is a rough game plan, I'll make this more precise in the coming slides, is to generate, first of all, to generate an ensemble of simulated events. Some events will have cores, quark-matter cores, some will not. We'll look at a bunch of different candidate MR curves. And then we're going to look for kinks in the M1, that's supposed to be M1, F of M and lambda tilde plane, where F is some function that I'll specify here in a minute. So we're going to look for kinks that are distributed in the MF plane and the chirp mass F planes for some choice of F. And we're going to then quantify the number of events that will be required to observe a given kink size at a given critical mass. Okay, so I just want to go back here to this slide right here and just say the kink size here is determined by what your hadronic equation of state is, as well as the latent heat and the sound speed of your quark-matter equation of state. So once I specify, for example, how big of a kink I can resolve, that'll translate into parameters like a sound speed and a latent heat for the quark-matter phase. So let's look at hadronic MR curves here for a minute. This is a plot that I've stolen from this paper by Ozil in 2016, where she plotted the MR curves for a large collection of microscopic equations of state. You see here that there's considerable uncertainty in the radius. The theoretical calculations that are used to generate these MR curves are yielding considerably different results. You should regard that as a signature of, well, signature is right. It is a consequence of the fact that the theoretical calculations that generate these curves have considerable uncertainties in them. The microscopic equations of state are unknown. Nevertheless, in the 1 to 2 solar mass range, almost all of the MR curves here, at least all of the ones that yield neutron stars greater than 2 solar masses, have MR curves that are nearly constant in radius. The radius is 10 kilometers or 12 kilometers or 14 kilometers or so on. The MR curves here are approximately constant. So what we're going to do in our analysis here is because of this, we're going to restrict our attention to neutron stars in the 1 to 2 solar mass range. And instead of playing around with this equation of state or that equation of state, we're just going to use a piecewise linear approximation to MR curves, where there are 2 linear segments. Because that right there will turn out to be sufficient to approximate our hadronic MR curves. Okay, all these curves are basically constant. So if I approximate them with 2 straight lines, I'll be doing a good job. And I'll quantify this at the end of my talk. So there's our hadronic MR curves for some choices of parameters P0 through P3. The parameter P0 will turn out to it's just an offset, a radial offset, and it'll turn out to be irrelevant for our analysis simply because we're only looking for kinks. We're not looking for the absolute radius of neutron stars. For hybrid MR curves, we'll also use piecewise linear approximations. And the piecewise linear approximation will be, the hybrid curve will be equal to the hadronic curve at m less than mc, which is physically motivated by the fact that the hybrid, there's no quark matter, so the hybrid and the hadronic curve should be the same. And that at m beyond mc, we'll just use a straight line. And so a cartoon of this is shown in the lower right-hand plot here, where our hybrid MR curve just has 3 piecewise linear segments. I'll note that if m is less than this first kink that appears down here, it'll only have, of course, 2 piecewise linear segments. Okay, everybody happy? Everybody's on board? Okay, good. And again, I'll quantify how good of approximation this is just using these piecewise linear curves at the end of my talk. So a useful observable to employ here is of course not lambda tilde, but some function of lambda tilde. Here's the expression for lambda tilde I wrote down earlier. And here's this relationship that I told you earlier as well between the compactness and lambda, which is universal. If you take this relation and you expand it about m1 equals m2, so r1 is equal to r2, and I'll call that common radius the inferred radius, a little bit of algebra can show you that that inferred radius is related to the chirp mass and lambda tilde as follows in this simple equation that I've written down here. So this equation for this inferred radius turns out to be a very good approximation to the radius of neutron stars if the MR curves is constant. Okay, so if we go back to this slide right here, for these MR curves that are essentially vertical lines here, if we collide two neutron stars there with one of those MR curves as the MR curve of the neutron stars, then this inferred radius gives you a very good measure of the actual radius of the neutron star. So you can determine the radius from the chirp mass and from lambda tilde, two things that LIGO can measure. Now, on the other hand, if there is a kink in the MR curves, so for example, this scenario right here in the lower left-hand corner, if there's a kink in the MR curves, the radius of neutron stars is not constant, and this inferred radius here is not a good approximation to the actual radius of neutron stars. Nevertheless, its value lies in the fact that if I measure a chirp mass and a lambda tilde, I can plug them into this formula and determine whether or not there's a kink in MR curves. So what I'm telling you is forget about the actual radius of the neutron star, forget about whether or not this formula is a good estimator of that radius, and rely on this formula only for detecting kinks, not the actual radius in and of itself. Is everybody on board with that? Does anybody have any questions? Because this is crucial for the rest of the talk. So what I mean, to be a little bit more specific about this now, suppose I take one of my two of my piecewise linear curves here, a hadronic MR curve and a hybrid MR curve. And then I look at the density of events I should expect in, say, the chirp mass inferred radius plane or the M1 inferred radius plane. This is what you'd expect for the density of events. And let's just focus on the top line for the moment, the top two plots. What you see for the hadronic equation of state, sorry, for the hadronic MR curve, is that the inferred radius is approximately constant. It's 12 kilometers, basically. And that's because my hadronic MR curve here is nearly constant. It has nearly constant radius. So my inferred radius is really giving me a decent estimation of what the actual radius of my neutron stars are. There's no pronounced kink in the hadronic MR curve, in the hadronic, in the density of events in the upper left-hand plot. On the other hand, if I look at one of my hybrid models here, you see there's a pronounced kink in the density of events in the R inferred chirp mass plane. Once I get to about 1.4 solar masses for this particular set of parameters, there's a huge kink, and the density of events goes all the way down to 10 kilometers. Okay, and the same sort of thing happens also in the M1 plane, although the distributions are a little bit more broad. The bottom line message that I want to convey to you here is that this observable, this inferred radius, is very sensitive to kinks in MR curves, and in particular, MR curves that have large kinks, that are hybrid models in particular, will give you downward trends at large chirp mass or mass M1 and large kinks. Okay, so that's why this is a useful observable to look at. So what are we going to do? We're going to take data in the chirp mass inferred radius plane and the M1 and R inferred planes. These are the same plot that I just showed you on the previous slide. And we're going to do something super simple-minded, which is just fit piecewise linear curves, these black curves here, to the distribution of events that we measure. Okay, super simple-minded here. Okay, we're going to select events as having quark-matter cores if the following two conditions are met. One, the first condition, A, is that the rightward slope is negative, that it's decreasing, okay? Meaning that the radius of the neutron star is becoming smaller as the mass is increasing here. The second selection criteria is that the slope discontinuity between the two piecewise linear segments here is greater than 1 kilometer per solar mass. Okay, and we're going to say that if these two selection criteria are met, then you have a quark-matter core. Now, what you're probably thinking right now is that these two selection criteria are completely arbitrary, and that is absolutely correct. You can use a more stringent selection criteria. You can say, for example, that the right chirp mass slope is less than 1 kilometer per solar mass instead of less than 0. Or you could change these numbers however you want. When you do that, you might identify quark-matter cores with more confidence, but then you might miss some events that actually have quark-matter cores. So this is arbitrary. This is the choice we've made. It works. There may be better choices that you can secure. So simulation parameters here. We're going to the actual distribution, the mass distribution of neutron stars outside of the Milky Way galaxy is not known. It depends on things like, for example, the host galaxy metallicity. It may turn out to be the same as that in the Milky Way. It may not. I would expect this is something that LIGO will eventually be able to answer, what the actual mass distribution is. But for the moment, in order to just make the most optimistic of predictions, let's assume just a uniform mass distribution between 1 to 2 solar masses. We're going to assume Gaussian errors on the inferred radius and the masses, and we're going to weight those errors by a simulated distribution of signal to noise, which is tuned such that an event like GW170817 has an error on the radius, the inferred radius of 0.75 kilometers, and an error on the masses of 0.1 solar masses. So events that have less signal to noise will have errors that are significantly larger than this event, which was probably the most pristine event you could imagine seeing. We'll look at a whole bunch of piecewise linear MR curves. I won't bore you with all the parameters. I will just plot here. If you look at this plot, you'll see that there are 4 MR curves generated by microscopic equations of state: SLY, AP3, MPA1, ALF2. Here are some piecewise linear curves which approximate those, as well as some other piecewise linear curves as well. I'll talk later on about how well these approximations actually work. We'll look at a range of critical masses between 1 to 2 solar masses, and a range of hybrid branch slopes, alpha, between 0.5 and 8 kilometers per solar mass. So you generate a bunch of events. What do you get? So here is one set of events for a hybrid model, this hybrid model that yields this density of events in left-hand plane, left-hand two plots here, both in the inferred radius and chirp mass plane and the inferred radius and M1 plane. That's without errors. With errors, what you get is on the right-hand side. And so you see that it's very difficult to decipher whether or not there's actually a pronounced kink in the data. I should say also that there's no errors on the chirp mass because, again, the chirp mass is measured with decent fidelity by LIGO. So it more or less looks like a bunch of scattered data. Nevertheless, there are trends present there. If you do this a whole bunch of times, you can actually extract those trends and see how well our selection criteria actually identifies quark-matter cores. So the first thing we're going to do is inject into our simulations hybrid injection data that actually that has significant kinks in it. And what we're going to do here, what I'm plotting on the right-hand side here, is 1 minus the fraction of events that have the rightward slope in this piecewise linear fit here being positive. Remember, I told you that hybrid models, that slope should be negative. So let's plot 1 minus the fraction of events where that slope is positive. With hybrid injection data, that gives you the confidence of excluding a general hybrid model that has some hybrid slope alpha as well as some critical mass MC. And so this plot here was generated with 40 detections, which is not that much. That's roughly how much LIGO is expected to observe per year, 40 mergers or so. Maybe it'll be 20, maybe it'll be more, but it's roughly how much you expect it to observe in a year. So what you see here in this plot is that with just 40 events and this very simple selection criteria, you can reach up to 80% confidence of exclusion here. And so in particular, the confidence of exclusion is greater when alpha is greater, when your hybrid branch slope is greater, and the critical mass MC is smaller. And that's just simply because it's easier to resolve a kink when you have a greater slope and the smaller critical mass. Okay, so when your MR curves have that hybrid branch being almost horizontal here, it's really much easier to resolve the kink. So that right there is nice. You can exclude models of quark-matter with just a handful of events. And as I said to you earlier, even though I'm just using these simple piecewise linear curves, if you specify your choice of equations of state, you can translate the size of the kink as well as the critical mass into where the phase transition is at, and latent heat and the speed of sound in the quark-matter phase. You can translate these parameters, alpha and MC, into physical microscopic parameters in your equations of state. So that was for excluding hybrid models. What about for identifying quark-matter? So here what we'll do now instead is inject hadronic MR hadronic data, so this data that doesn't have any kinks, any significant kinks in the MR curves. And what I plot here is 1 minus the fraction of events that have slope less than 0 and slope discontinuity greater than 1 kilometer per solar mass. That was my selection criteria for quark-matter. And so this measures the confidence that you will identify something as having a quark-matter core. So as a function of the number of detections, what you see here is that our most pessimistic model, and I guess it's model D here, as if you know what model D is, I didn't tell you. Our most pessimistic model yields about 70% confidence of identification at only about 100 of events or so. And so that's telling you that the fidelity at which you can at least say that there is a quark matter or some exotic matter present in neutron star mergers. You just have to observe, you know, some handful of events, you know, on the order of 50 or maybe 100 events to be able to say anything with any degree of certainty here. That's nice. What about identifying the critical mass, reconstructing the critical mass? If I look at the actual distributions in the R inferred M planes for a hybrid model, if you go ahead and roll up your sleeves and do the pencil and paper calculation, you'll see that the distribution of events has a kink at chirp mass equals to the critical mass divided by 2 to the 1/5, and that in the R inferred M1 plane, the kink occurs at M1 equals just MC. And so you can then take our fits here, just as a rough estimator, our piecewise linear fits, and use the location of the kink as a rough estimator of the critical mass. And so in this plots that I'm showing you at the right here, I'm not going to, I'll just say that they should be 1 if we were reconstructing the critical mass perfectly. This procedure we are using here has significant systematic errors. They're on the order of 10 to 30% or so, and this is due to the fact that what we're doing here is just too simple-minded. We're fitting distributions to curve. We're fitting curves to distributions, and obviously, even though the distributions themselves have kinks at a specific location, because you're fitting a curve to a distribution, the curve itself won't have a kink that occurs at the same place. That I hope is clear. If it's not, you can raise your hand and ask me about it. Let me see here. So future improvements to this analysis. I think the obvious thing to do is to fit distributions instead of piecewise linear curves. Once you specify an MR curve, the distribution of events is fixed, at least with the additional information of knowing the actual neutron star mass distribution. So once LIGO has observed enough events to where we have a decent idea of what the actual neutron star distribution is, this is something that is reasonable to do. Okay, but until then, I think that you have to make too many assumptions for it to be fruitful, which is why we didn't do it. Good. Now I want to come back to this point here that we've used piecewise linear MR curves. If you've spent your career developing microscopic MR curves, you might think, you guys should have used the actual microscopic MR curves and not these silly piecewise linear approximations. So what I'm showing to you here in these two plots is the exact density of events that you get if you use 4 different microscopic MR curves for hadronic matter versus their piecewise linear approximations. So there's the SLY MR curve, which is this magenta color. There's the AP3 MR curve, whose linear approximation is cyan. There's the MPA1 MR curve, whose piecewise linear approximation is dark green. And there's ALF2 MR curve, whose piecewise linear approximation is yellow. In this colored plot here, are the density of events that you get for the exact microscopic MR curves. On the right-hand side are the densities of events that you get for the piecewise linear approximations. The key thing that I want you to take note of here is that the density of events only differ over scales which are much less than 1 kilometer. where they're inferred radius. They only differ over inferred radii scale, which are much less than a kilometer. The observational error associated with the inferred radius is going to be on the order of a kilometer, maybe even a few kilometers for low signal to noise events. And so what this means is that you don't really gain anything by using the exact microscopic MR curves. The piecewise linear approximations are completely sufficient. And if you also look at for example, hybrid MR curves, you reach the same conclusion. This right here is for the hybrid MR curve that I showed you in the very beginning of my talk, which was MPA1 connected onto a constant sound speed equation of state. The left is the exact density of events. The right is the piecewise linear approximation. And you see that there's essentially no difference that you're ever going to be able to resolve. And so the piecewise linear approximations are sufficient. Now that is, in my opinion, nice because it makes everything that we're doing model independent. We didn't need to actually specify any equations of state in this analysis. I could have equally well called this talk, instead of calling it detecting exotic matter, I could have equally well just called it detecting kinks in MR curves with LIGO, because at the end of the day, the kink is the signature of the exotic matter, and it is the primary observable that we're actually after. So with that said, I'm done, guys. Future directions for this, the first two things I've already told you about. Employ mass distributions from data. Uniform mass distributions are probably not correct. I wouldn't bet anything that they're correct. It is, again, the most optimistic of scenarios. After LIGO publishes a paper, which hopefully will happen relatively soon, with actual distributions, you can generalize this analysis and use data for the actual mass distributions. The other thing that I've mentioned as well, instead of doing this really simple-minded fit, where we're fitting piecewise linear curves to data distributed in the M1R planes and chirp mass R inferred planes. Instead of fitting to those curves, we actually fit to the distributions themselves. And the last future direction, which I think is very interesting, and I'm not going to say anything about it because I don't want any of you to scoop me, is to study post-merger dynamics. What happens if you look for signals after mergers? Unfortunately, with current detectors, the post-merger signals are out of LIGO's bandwidth, but hopefully we'll be able to see that in the not too distant future. So with that said, thanks, guys. I'm done. Retardation effect.
Super. So there were a few questions during the talk. I've seen some number of neutron star experts. Do we have more questions from the audience?
I didn't see any questions. I'm sorry.
No, I'm asking if there are more questions from the audience.
So yeah, maybe one question. In your analysis, would it make a difference if you assume a neutron star with like a quark matter core versus like a pure quark star that are also postulated?
Yeah, so a pure quark star would not have a kink in the MR curve. Okay. Right. So if I go back now to this slide, way back right here, okay, that kink is arising due to the fact that you have a core that has different physical properties than the hadronic matter that surrounds it. Right? So as soon as you nucleate a core, there's a discontinuity in the MR curve due to the fact that there's a latent heat and that the speed of sound is different in the quark-matter core. So that right there is the primary observable that we're looking for, the kink in the MR curve. If the whole star was quark matter, well, the MR curve probably looks nice and smooth. There's no kink. So my answer is this analysis will not see it.
Okay.
Further questions?
I mean, it seems that the strand of this analysis is that it's very universal, right? And like you seem to, I mean, I'm not really an expert in this field, but like it is like you displayed a large number of models, and like all these models had this almost flat behavior, right? That you can piecewisely approximate by 2 segments, right? But do you have, I mean, can you pursue this analysis further and somehow be more distinctive between models?
Sorry, I don't exactly understand what you mean, more distinctive between models.
I mean, say you have like 10 models, right? They differ. Can you say which one works better? Or like the only thing that you can answer using that sort of analysis that you're doing is if there is a quark-matter core.
Are you asking, can I distinguish this MR curve from that? Are you asking that?
Sorry, can you repeat the question, because there was a breakdown in communication.
Can I distinguish one MR curve from another?
Yeah, exactly. Yeah.
I don't think so. I don't, at least not with what we're doing. Maybe somebody else can come up with something that'll do that, but I don't think that our analysis does. All that we can, our primary thing that we're coming out with here is the confidence in which you can say there is an exotic core or there isn't. That's it. I think to really to say something with more precision, you really have to measure the MR curves more accurately. There are curves, basically this. I don't have them at my fingertips. So, but our analysis is not sensitive to the details of the MR curve. So in particular, I can just tell you that our analysis doesn't care anything about the overall radial offset of MR curve. It is sensitive to kinks.
Yeah, sure. No, I got it. Yeah.
Not the absolute radius. Right? So we're not doing a reconstruction here. We're not trying to reconstruct the MR curve. We're just trying to ascertain the fidelity in which you can actually identify the presence of an exotic state of matter.
So I have one question. So you mentioned that you will be in the future hopefully using some observational information regarding the mass distribution of neutron stars, but then there are also all these attempts to do simultaneous mass radius measurements using, for instance, X-ray observations. So far there are only a handful of measurements and the quality is not great, but I suppose that you could also constrain some of your parameters by using sort of non-gravitational wave related mass radius measurements. Have you thought about that?
I have not, but others have. I know that Ozil, for example, has a lot of papers on this. But let me just, one major advantage that LIGO has over those methods. First of all, they rely on a lot of theoretical. And second of all, LIGO will observe a constant stream of, which is just going to add up over more and more time. Whereas there's only so many neutron stars that are easily observable in the Milky Way. I would expect it like to get far more data than what's available in over. At least that's my guess. Right. So you don't have any assumption about how long or how there's any material around the neutron star that might absorb radiation. You're just studying gravitational wave, which are to the there's far fewer assumptions that go into it.
Do we have some more questions from the online? Oh,
yeah. So another question is, so because you particularly put the quark-matter to a very significant place, but for example, is there any possible other type of phase transition, like you mentioned, hadronic matter, or for example, some resonant resonant state, this transition resulting in similar observation, for example?
I think the one thing that we can be certain of is that there is a paper on the archive where somebody claims so. That's the only thing I can tell you with certainty. There are papers studying hyperons that also give you kinks as well. The equation of state, again, the speed of sound changes when you get a hyperonic core. My understanding is that including hyperons makes it really difficult to have neutron stars that are 2 solar masses or larger. So currently, the maximum observed mass is 2.17 solar masses with some non-negligible uncertainty. I'm not aware of a plethora of hyperon equations that are consistent with this. Now, that being said, there are in the interactions, and I think that say that these scenarios are out by any means. And so, with that said, you can happily replace the words quark-matter with exotic matter. I think that might be a more agnostic approach to this, that would really identifying exotic cores. But again, I will cover my own behind. I will say that as far as I'm aware, the hyperonic equations are not, at the moment, not consistent with 2 solar masses.
And yeah, so just another comment, because so you may know that Professor Masaru Shibata once had a paper about if you have spontaneous scalarization of the space-time. So basically it's a scalar tensor theory. For example, if that could happen when you have presence of high density matter, which is very similar because here you have high density and then matter have a phase transition. But yeah, in some, for example, modified gravity, you could have a phase transition of the space-time structure when you have high density. That could result in a similar observation of phase transition happening for the matter. So I'm wondering, for example, also whether that degeneracy could be broken also with similar method. But yeah, maybe it's something to be considered in the future, I think. Say if such, for example, with those amount of gravitational wave signal is detected, and whether you claim you see a quark core, whether you claim you see the evidence of alternative theory, right? So something like this.
Yeah, I mean, the only thing you can really say with absolute certainty is that you see a kink.
Yes, yeah.
And everybody can debate about what caused that kink.
Yeah.
Right.
Yeah.
Right.
Thank you.
Do you have 1 or 2 last questions from the online audience? Okay. If not, thank you, Paul. I'm gonna turn